Okay, so today we start to have some payoffs for the abstract stuff we did today. And the first thing I want to talk about is what are called physical invariant measures, or absolutely continuous invariant measures. So I'm recapping at the beginning here. I'm saying in the deterministic setting, I'm back in the deterministic setting. Quasi-compactness tells us that we can have one or more elements outside this essential spectral radius disk. And these are going to be the interesting ones. And for Perron-Frobenius operators, we will always have an eigenvalue 1 by construction. And if you impose some mixing or covering assumptions, I discussed covering at the beginning of last lecture, you can ensure that this eigenvalue 1 has unit multiplicity and it's the only eigenvalue on the unit circle. So for simplicity, I'm just going to stick in this situation. Okay, so if you have an eigenvalue 1, obviously this is a fixed point of the operator. So what this says is it's some function which when you push it with the transfer operator, you get the same thing again. And also you can show that this is non-negative. It's a consequence of the Perron-Frobenius theorem, which is a general theorem about Markov linear operators. And if you L1 normalize it, then you can think of it as the unique invariant density of the map. So let me just explain why this is. I think everyone who's in dynamics knows this stuff. So let's say you have some observation function G. So this is some, excuse me, some real value measurement on your phase space. And you can form what's called a Birkhoff average. So this means you pick some initial condition. You measure the output of G, whatever it is, G might be temperature or something, at that initial condition, and then you start iterating your orbit. And as you go along the orbit, you keep evaluating G, and you just simply take an arithmetic average of the numbers that are output. And then you can let the orbit go to infinity, and you hope that you have some limit. So this is called a time average. And by Birkhoff, which was mentioned by Igor and Steve, I think, this is equal to the integral of your observation G against this phi 1, this leading eigenfunction of your transfer operator. And this is equal for Lebesgue almost all x in the support of your phi 1. So this is very convenient because this might be expensive to evaluate, but if it's often cheaper and more rigorous to evaluate your phi 1 if you want to control errors. And so if you're interested in these averages, often this is a more controllable thing to compute. Also, as mentioned by Igor and Steve, is you can do a spectral decomposition now. So we've talked about eigenfunctions, quasi-compactness, and so on in the spectrum. So if I were to take some general f in my Banach space, and I start pushing it n times, and then in the current setting, what I expect is that I will equilibrate. And I will equilibrate to some multiple of phi 1. And what the multiple is just the integral of the function f that you're pushing. So if you take that away to see how fast will I equilibrate, then what's left is just the remaining sums of the other isolated eigenvalues raised to the power n, their corresponding eigenfunctions, and then this sort of rest, which is described by some operator q, and the spectral radius of q is bounded above by the essential spectral radius of L. So everything in here is decaying faster than the essential spectral radius bound. So this is stuff that goes away very quickly, and this is stuff that also decays, but at slower geometric rates. All right. So now, just for a little intermission, let's do some computations. So I'm going to do the yes.
Why do we know 1 is the only eigenvalue on the unit circle?
Well, I didn't prove it, but because of these mixing or covering assumptions. Okay. If you have an interval, if you can choose any interval and it expands over the whole interval, then you can't have disjoint pieces of the interval that somehow do their own thing and would generate two invariant measures. Okay, so yeah, a very old way of estimating this phi 1 is that you take your state space, let's say here 0, 1, and then you partition it. 0, this is 1, and you partition it into subintervals like this. So if, let's say I have n of them, so the width here would be 1 on n. And I want to consider the action of L on the subspace spanned by the indicators on these subintervals. So I'm going to build approximate functions as say steps like this. Okay, this would be a typical function in that subspace. And I define a projection onto this subspace pi n, which is, we just take the conditional expectation of f on the ith subinterval, and that's your coefficient for the ith indicator. And I'm not going to derive it here, it's not difficult, but it takes several lines, that the matrix representation of pi n acting on L, true L, is given by this expression here. So you have a nice expression in terms of the subintervals themselves and their preimages. Okay, so if we want to compute this, obviously this numerator here, I could write as the integral of the ith indicator multiplied by the indicator on the inverse image of ij. And then by properties of indicators, I could take this T inverse and make it a composition of T. And now my indicator is on ij instead. And this one here I just turned into integration over ii. So if we can perform these integrals here, then we will construct the matrix Lij. And so I could not resist to put some Julia code here. Some people
what a surprise.
So let us do this for this particular map. So here we define a map, which is pi x mod 1, which we looked at before. Let's have 200 subintervals. And now I define my jth indicator. So I want to define an indicator on this region here. So if x is sitting between j minus 1 on n and j on n, then I want to get a 1. And if not, I want to get a 0. So this is a function of an integer j, and what it outputs is a function. It outputs an indicator function. So it outputs the function that is x to this indicator. This itself would give a true false, and if you put a float in front of it, you get a 0, 1, or 1, 0 instead of a true false. Okay, and now we want to compute the integral that I talked about. We want to compute this. This thing here is going to end up being just multiplication by n, because all my subintervals I'm dividing by 1 on n, so that will show up as here. That's the multiplication by n. And then what am I doing here? So quad gk, this is just a function that does integration. It does Gauss-Conrad integration, which is a higher order scheme. Here's the function I want to integrate. Remember, the indicator on j composed with t. And I want to integrate over the subinterval I minus 1 on n to I on n. So the syntax is the function you want to integrate, and then the left and right endpoints. What this outputs is a tuple. It will output the integral and the error, estimated error, and I just want the first. So that's why I put the 1 here, just to extract the first component of that tuple. Here I multiply by n, and then I want to do all these integrals for all possible ij. So I have this what's called a comprehension here, And this will create a matrix for me of size n by n, looping over, looping I and j over 1 to n. Okay, now I think I've set this up so that you can just copy paste this into, if you open it with a reasonable PDF viewer and you have a reasonable code editor like VS Code or something, you can literally copy paste what is in the PDF and all the symbols will be faithfully copied over to the code editor. I tested this morning, the entire thing, and it works. Okay, so let's see how this looks. So I will define my function and mouse especially. Define my function, make a scatter plot of the function. Okay, so there's a graph of my function. It's pi x mod 1, right? So I have these 3 full branches and then a partial branch. Now I want to say what is n, and I define my indicators, and then I want to compute this. Matrix. Okay, so I get a 200 by 200 matrix. We can visualize this as a heat map. So this is a 200 by 200 heat map plot, and you see the same kind of structure. You see the 3 full branches here and the partial branch. So this is a visualization of our Ulam matrix. Then, okay, maybe I go back to the slides. Now what we want to do is compute the leading eigenvector. So I'm just going to compute all of them. So let's say lambda phi is this is the left eigenvectors of L prime, sorted by magnitude, descending magnitude. And we want the top one, we want the first one. So let's do that.
L prime?
Because the Ulam matrix, I guess I'm giving you the classical Ulam matrix, and it is interpretable as a Markov chain, and classical Markov chain theory has the leading, so the invariant measures given by the leading left eigenvector.
Just the transpose of
which is what I did with the, yeah, that's what the prime means. The prime is the transpose. Okay, so there are my eigenvalues. You can see the leading one is approximately 1. And then I have some others. So let's see what they look like. So here I just scatter lambda. So excuse me. So this is 1. This is the rest. For this map, we have some theory to say what the essential spectral radius bound is. So let's plot that. Our slope is everywhere pi. So what should be the bound? Yeah, so let's plot then. So what I'm doing here is plotting parametrically. So the x-coordinate is theta goes to cosine theta divided by pi. I'm trying to plot a circle of radius 1 on pi. And the y-coordinate is the parametric function theta goes to sine theta divided by pi. And I want to do this from 0 to 2 pi. So I'll plot this over the top in red. Okay, and there we are. So what we see is that you have this eigenvalue 1, and so you have this eigenvalue 1, and then in this case, excuse me, the remainder of the spectrum is contained inside this essential spectral radius bound.
There seem to be some isolated eigenvalues within the essential spectral numerical.
Well, by definition, I'm defining them as not isolated if they're inside the dotted red line.
Okay.
I mean, I could have a larger n in it.
Okay. Okay. So it's the reason is the discretization. So if you increase n, okay.
Let's just get the leading. So this phi that I got from eigen, that's an array where each column is an eigenvector. The first column is the one we want, so I extract here the first column and normalize it by its mean. Okay, so that's a 200 vector, and then we can plot that on 0, 1. And so this is what our estimate of the invariant density looks like for this beta map for pi x mod 1. So if you were to run long orbits and make a histogram, the histogram would look like this. You would spend a little more time near 0 and less time right of 1/2. This is very likely not a continuous function, but it's a BV function, and we're working in BV. Now, I should mention the Gaia package, which April is developing with Oliver Junger. So Gaia has been around for a long time. So originally it was developed by Michael Dellnitz and Oliver Junger in C, I think, and then around 2000 they wrote it in some obscure language called Python, and then they used that version, and then now they've also Julia fans, I think, been writing it. have a Julia version, which is very nice. And Carolyn, you also have a package, right, in Julia? Where's Carolyn? Not here. Okay. Okay, the package is called Poltergeist, I think. So it's designed for smooth or real analytic 1D maps, I think. Gaia was doing multi-D. I put a link here to a 1D example closest to the sort of setting we're looking at here. Okay, now I want to do this in the random setting. So again, in the random setting or the time-dependent setting, we're changing our map all the time. And actually, this reminds me that yesterday April had a question about what sort of maps this applies to, and I said something like they should be expanding, or maybe the slope can approach 1. But in the random case, all we need actually is that I'll go back to this quasi-compactness condition. What's the best one? Yeah, this one. So this R that you would get is random. So I could have, for example, something like T1 of X. I'm using notation here, but I'll have 2 maps. Okay, so T1 of X might be 2X mod 1. And T2 of X might be, say, X on 2. It's obviously contracting. And you can randomly apply these, concatenating them to make a sequence. The 2X mod 1 one will have an R here of a half. The half one will have an R here of 2. And all that really matters is the proportion in which you apply these. So as long as you apply this one slightly more than this one, then you're good, and your cocycle is quasi-compact. And it doesn't even depend on the memory in the driving. So you could choose these with a coin flip according to some Bernoulli process, or you could choose them according to, say, a circle rotation, which has very long memory. And it doesn't matter that for the quasi-compactness of the cocycle, all that matters is that as you start concatenating these things, in the long run, the frequency of each is what matters, whether it's quasi-compact or not. So the random setting is really much more general, because you can throw in all sorts of nasty maps that you could not otherwise use, as long as they're compensated by sufficient expansion. Okay. Yeah, so back to the random set. So what we saw before when I talked about these Dirichlet spaces was that the leading one, for example, would transform like this. You take E1, the subspace, you hit it with L omega, and the omega E1 transforms to the E1 on the next fiber. And now, if each one of these is spanned by some single function that I'm calling phi. So phi omega comma 1 is the single function that spans E1. And I can collect all these up into a collection where little omega is in big omega. And then collectively, I'm going to think, if I normalize these on each fiber, collectively, I think of these as a random invariant measure for the random system. Okay. yeah, you had a question about why. So the analog of your question, why is the eigenvalue 1 the only thing on the unit circle? The analog of that in the random cases, why is the Lyapunov exponent 0 having unit multiplicity? And something that will enforce that is a random covering condition. So you pick an interval J, and you want to then apply your cocycle, your random cocycle to that J, and if you always expand to the full interval, then so this means that even random driving realization wise, there's no components that you are isolated to because you expand everywhere. Okay, so this is how this, if I write it for functions, it will look like this. So the L's are Duron-Frobenius operators. They will preserve the L1 norm. So if you take an L1 normalized density and you push it forward, you get another density. All you have to do is update the omega. So you can write down a spectral decomposition now. You can say, in analogy to what we had before, you can start with some F. You now start pushing along your cocycle of operators. And if you push n times, then what you expect is you relax, you equilibrate to phi sigma to the n omega. And how fast you do that is given by the remaining Lyapunov multipliers. So this notation here is defined here. So what I'm doing is just multiplying along the orbit these Lyapunov multipliers. And what you have left is some random cocycle whose index of compactness is smaller than the kappa star we had before. So this is, I would say, a rather complete analogy to what you have in the deterministic case. You have the exceptional exponents here, and you have the rest that live inside the equivalent of the essential spectrum. Often you see this in random dynamics in a pullback sense. So instead of taking an F and pushing forward, what you do is you take your F, you go back in time, and you start pushing n steps in the past, and you push to the present. So you would start at phi bar sigma to the minus n omega, you push n steps, and then you expect to arrive at the invariant density at omega. So this is a little more convenient when you're proving limits because you just have this fixed object that you're converting to. Yes, okay, and I'm going to come back to these points later, but if you take let's say a random long word, if you pick some initial x and some initial omega, and you just run trajectories in random trajectories in phase space, you might ask how they distributed. And they are distributed according to the mean of the p-mean of these phis. They are not distributed according to the fixed point of the average transfer operator in particular, only if you're driving as Bernoulli. Okay, so if you want to find the physical invariant measure for your random or time-dependent system, you must compute these. You cannot short-circuit it by computing an average transfer operator. Okay, so that was the leading eigenvalue and the Lyapunov exponent. So now I want to talk about the second and lower ones. So I think this hyperlink is not going to work, but you can look in the notes. So I think equation 110. Okay, maybe I'll go back once. So equation 110, I think this was the Keller expression. Oh no, this one. Wait, then I think I want 1.2. So 1.2 was, so near the beginning, we had this expression for the essential spectral radius. And I guess the thing I want you to take out of this is that, remember, this is like 1 over the minimum sustained stretching that the map experiences. Here you have a single map, and in the random case, you would have an omega here. So it's either the single map or the cocycle. It's the 1 over the minimum sustained average stretching. So that's either the kappa star or we call it R or rho. Is the essential spectral radius bound. So if you have an eigenvalue of magnitude larger than that, then somehow, I mean, how is this eigenvalue generated? The eigenvalues that are smaller in magnitude than this essential spectral radius, they can be generated just by the decay of correlations due to the chaos, due to the local expansion of trajectories. Okay, so you have your local slope of your map. This tells you locally how fast trajectories separate, and this will make you decay at a rate like that. But if you're decaying slower than that, then there has to be some other structure in the dynamics that is causing this eigenvalue to be there. And so this is another reason why these isolated eigenvalues are particularly interesting and special. So let me show you an example of how this can occur. Here is a graph of a map. The slope, I chose it deliberately simple here, so the slopes are all 3. So the essential spectral radius should be 1/3. Note also that the way I designed it, the left subinterval here is approximately mapped onto itself. You have a little bit that leaks out here. And the right subinterval here, it's also approximately mapped to itself by this block, diagonal block, and you have a bit that leaks out here. So this presence, these things are called, these two intervals in this example, the subintervals 0, 1/2 and 1/2, 1. These are called almost invariant sets. So this is due to Michael Donis, Alter Junger, Christoph Schütter, and Peter Dorfhardt. And yeah, you would say that, for example, if you take the symmetric difference of the subintervals, this is small, so nothing much is leaving. Okay, what does that have to do with the eigenvalues of the transfer operator? So in the example I showed you, you can compute. In this case, you can really exactly compute because I made it a Markov map. You can compute that lambda2 is given by this number here, which is about 0.8. And that's much larger than 1/3. So you have some decay that is much slower than the local expansion. And what is producing this is exactly these almost invariant sets. So here's the corresponding eigenfunction. Unfortunately, the picture says F2, but this is phi2 in my notation I want to use. And look where it is positive and negative. It's positive on the first almost invariant set, and it's negative on the second almost invariant set. Why is this slow to decay? Because if you want it to decay, it has mean 0, and it should decay to the 0 function. How can it decay to the 0 function? You have to have the positive and negative parts overlapping and cancelling out. And if you only have a tiny piece here that is doing some cancellation at each step, you're going to get slow decay. Practically, the point is that you can, finding these blocks, okay, here in this picture it's easy, but in more complicated maps, finding these blocks is not so easy. But what you can do is compute your transfer operator, look at the large spectral values and their eigenfunctions, and see where they are positive or negative, or having level super or sub-level sets near to 0. And this will identify for you where these almost invariant sets are. So this is much easier than trying to search, doing a complicated nonlinear search in phase space. Okay. I guess also you can think about, so some work Cecilia has done is to think about the case where you shrink this branch down to 0 and you end up with 2 really invariant pieces. What happens in the limit? So that's been looked at. People applied this to all sorts of things. So very early on, people looked at almost invariant sets for molecular conformations. So these are physical shapes of molecules that drugs tend to sit in for long periods of time. You want to find them so that the drug can sit in that shape for long to interact with the receptor in your body for the drug to work. Astrodynamics, which Steve talked about yesterday. So finding these orbital regions, including the halo orbits for Jupiter, and also in the ocean, finding things like ocean gyres. So this is also work that Catherine's been involved in, and she is the P here, the citation, and the plus. Yeah, so for example, this was one of the early experiments where we took surface ocean currents from a model. We built the transfer operator from 2-month flow. And this is one of the leading eigenfunctions of the estimate of the transfer operator. And the important parts of the extreme values here in your, what I'm plotting is a graph of the eigenfunction, right? So your domain is this. And then I'm coloring according to the value, the real value of the eigenfunction. And you have these highlighted bits here and here, which are known gyres in the Weddell Sea here and the Ross Sea here. And oceanographers would typically try to estimate these by sea surface height. So they use what's called geostrophic assumption, which ignores wind. And you can look at level sets of sea surface height, and this is a proxy for the boundary of these gyres. But they ignore wind effects, which are very important, particularly around Antarctica. What did I want to say else? So yeah, what are these things physically? So physically, these are slowly rotating blobs of water, and they are really containing water that is largely distinct from the surrounding water. So here, coming through Drake Passage here, you have really a lot of turbulence, and this creates this very slow-moving vortex here. And this is dynamically disconnected from the water outside. So you have a slow decay. If you were to drop a bunch of food coloring or dye or something in here, it would take a very long time to meander out of here into the rest of the ocean. That's the slow decay that's being picked up by the eigenvalue. This was an experiment we did in 3D, so it's the same gyres. This is the Weddell one, this is the Ross one, this is the Falkland Islands, which is relevant for people in the UK. This is South America. This is Antarctica, and this is New Zealand with the North and South Islands joined, and this is Tasmania joined to Australia. And here we can see also the 3D depth. This was done with Ulam. You can really see the pixelation of the Ulam cells that were what was possible at the time.
Yes, been a while.
Okay. So now I want to go on. So I've talked about the leading eigenvalue, the isolated eigenvalues that are real, and now I want to talk about isolated eigenvalues that are complex. So here, instead of almost invariant sets, you expect almost cyclic sets. And yeah, I should say this is, of course, related to the kinds of complex eigenvalues that you would get from what people do in Köppen analysis. So as for the real lambda 2s, the rate of decorrelation is given by the magnitude of your complex lambda 2. And the argument, something you don't have in the real case is an argument. So the argument determines the period of the approximately cyclic motion. So if we write the lambda 2 in polar form, then the R, which is going to be less than 1, is the geometric decay rate. And if I write it like this, then alpha is, so you're advancing through a complete cycle, a fraction alpha of the cycle every time you apply the operator, every time step of the operator. So since you're advancing the fraction alpha of your cycle at each step, the period is 1 on alpha in units of transfer operator time steps. Where the almost cycle is in phase space is indicated by high magnitude regions. So this is similar to what we had back here, right? These were high magnitude regions, so the same thing holds in the complex case. And maybe I show you an example with Lorentz. So here, I mean, this is a non-rigorous, I should say, experiment. So here we compute an estimate of the transfer operator for Lorentz from the trajectory that you see here. And on the left, and then you have the eigenvalue 1, of course, and then the next eigenvalue is a complex conjugate pair. So I take one of those and I plot the magnitude of the corresponding eigenfunction. So you see you have a dark blue around kind of the center of the wings. In red here, what I plotted is the lowest periodic orbit, just for comparison. On the right is the argument of the corresponding eigenfunction. And this is meant to be in a cyclic color scale. So this is minus pi to pi. And so what happens as you go around the wing like this, you complete one circuit of the cycle that's indicated by the argument here. So the cycle, this dominant almost cycle that we're pulling out is the bulk motion around the wings of Lorentz. It maintains the symmetry. So it's not completely obvious, but it satisfies the symmetry that Lorentz satisfies. And I will show you
Lorentz cycle.
authentic Okay, so on the left you have the trajectory. In the center you have the same trajectory, but I'm plotting in color the argument. So it's the same picture I had on the slides. And on the right, what I'm doing here is plotting the same color. The black dot is the same black dot. I'm plotting the same color, but instead of plotting the dot on the attractor, I plot the dot at the location of the value of the eigenfunction in the complex plane. So the way this is constructed, in this case from a time series, let's say I have 10,000 points. So I have this big, let's say 10,000 by 10,000 matrix that I compute an eigenvector of. So its eigenvector has length 10,000. Each entry is a complex number. And as I proceed down in time along this eigenvector, what I'm doing is I'm plotting the complex number in the complex plane. So you are, when I get back to away from the movie, I'll write down something slightly mathematical. But what you're doing is you're projecting, your eigenfunction is projecting from the attractor down to the complex plane. The eigenfunction is a map from the attractor to the complex numbers. So you can view it as projecting the cycle from the attractor to the complex plane. And this over here is the image of that projection.
Sorry, can I ask in the last one, this order is just as you go down?
Yeah, it's along the time series. Yeah, so it's a trajectory, like the black dot is the same in all pictures. And I'm following a trajectory. I think I'll restart this movie because for some reason it goes buggy after one loop. What did I want to say? Yes, and the last thing I want to say is that notice the speed in Lorentz is non-uniform. Okay, so you tend to go faster out here and slower here. The speed here is uniform. So when you do this projection, you also rectify the cycle. So the period alpha that we get is the period of the entire cycle. But here it can be a nonlinear cycle. It's not simple harmonic motion, but it gets mapped to simple harmonic motion by the projection. Okay. You can do this in high dimensions too. So these are some results for the El Niño Southern Oscillation. So the El Niño Southern Oscillation is a climate oscillation that oscillates between warm water in this tongue in the Indo-Pacific to cool water. Very roughly speaking, I mean, it's a very noisy, actually I should mention Claire, who's even much more expert than I am on, so please chime in if I say something silly. This is work with Dimitris Giannakis, who will turn up in week 3, I think. And yeah, this is a very rough oscillation, and what we're doing here is using points as images of sea surface temperature. So this image might contain between 5,000 and 40,000 pixels. So you think of this as a point in high dimensional space, and you're building your transfer operator in high dimensional space. This is obviously non-rigorous. But when you do this, your leading non-trivial eigenvalue is a complex conjugate pair that corresponds to this Enzo cycle, and you can represent the cycle not in configuration space like Lorentz. Lorentz is only 3D, but we can represent it in the observation space that we built the transfer operator from. And this is an example of the cycle that we extract, which you'll have to trust me is reasonable. And we also can get the average cycle period, which fits with what is expected. And in fact, we believe this is a better version, a better and more predictable version of a strong Enzo cycle, because we are really emphasizing the cyclicity of the cycle and the slowness of the decay. So I don't want to overclaim, but this correct phasing may lead to better predictable Enzo. All right. So now I want to do all of this in the random set. This is okay. So here is a recall, mainly with notation. We had these exceptional Lyapunov exponents here for our transfer operator cocycle. They can be written like this, where these were the multipliers that I had when I was doing the spectral decomposition. Since I have a log of these things, I can write this as a Birkhoff sum of logs. And since this is a Birkhoff sum, it's a Birkhoff sum on sigma, right? So P is invariant under sigma. So I'm using now the ergodicity of the driving. So I can write this as the integral over P, the average of the log of these multipliers. And this should be bigger than the kappa star, the index of compactness that we had before. So this should be a property of lambda I. It should be bigger than kappa star to be exceptional. Now I want to argue that, I want to make a similar sort of argument. In the deterministic case, I said isolated eigenvalues were special because they describe decay rates that are slower than local expansion can explain. And the same thing is going to be true in the random case. I have my random cocycle of maps, which are on average expanding. And there is some sustained minimum expansion rate for that cocycle. And if I see a Lyapunov exponent that represents decay slower than that, how does that come about? Not from general chaos, not from local expansion, must be from some other geometric structure, some other structure. So it's the same principle. Yes, okay, so what I'm trying to argue here is this slower decay, therefore very interesting, and must be connected with some, the structures should now be random or time dependent. There's no reason that these structures that I'm talking about that are causing the slow decay, there's no reason that they should be fixed in time, because our dynamics is not fixed in time. The governing rules are continually changing. So these structures in general, they will also be time dependent. Okay, so this is some, what I'm describing here is an example. So maybe I show you the picture first. So to illustrate this, here are 4 expanding maps, and I made the slopes all ±3 to make things easy. And I am now concatenating these according to a subshift of finite type. If you don't know what that is, don't worry about it. It just means I have some way of concatenating them in a non-trivial way. Some maps will not be allowed to follow other maps. For example, I do not remember if this is just for example, it might be that T2 cannot follow T3, for example. So not all adjacent combinations are possible.
Why not?
To make it interesting.
So the other would be like flipping coins, right?
Okay.
Yeah, it would be like flipping coins, yeah.
Okay.
Yeah, like the extreme case is if the driving's Bernoulli, and then you can follow anything by anything. But if you want really time, I mean, if you think about the other extreme, so shortly, I will talk about Lorentz driving something. So Lorentz is deterministic. And that's very constrained on what can follow what. Only some omega that's in a future trajectory of Lorentz can follow something before it. And at the other extreme, you have coin tossing. So this is subshifts of phenotype are somehow in the middle of those two. They're random, but there are disallowed transitions. Okay, so what I have done is, in my picture, I've made a sequence of the first six of these. So I've got 6 of these maps that I'm applying in sequence. And I compute the functions that span the oscillated spaces. And maybe I'll blow it up to that first. So here I'm using K here. Okay, so this is K0. Let's think of that as omega. So this is omega, this is sigma omega, sigma squared omega. It's basically sigma to the K omega. And on the omega fiber, this is the, I think it's in the caption, but since you can't see it, this is the phi 2 omega, or omega 2, depending on, I think omega 2. And this is the phi 2 sigma omega. Now, again, I split into positive and negative parts. What does the transfer operator do? Between here and here, between here and here, I have L omega. Between here and here, I have L sigma omega. So L omega will push this to this with some scaling given by the Lyapunov multiplier. But in the picture here, I rescaled everything, so the norms are the same. Then I take this and I push to this, and so on. And because of this positive subinterval will map mostly to this positive subinterval, will map mostly to this positive subinterval. So previously I had this, in the deterministic case, I had this map with these two blocks, right? And I had these 2 subintervals, 0, half, half, 1. And I said they are almost invariant. Now I allow the intervals to move over time. And the deep orange maps to the deep orange maps to the deep orange. If you want to see this in terms of maps, which we will do now. So now in a one-to-one fashion, I map this corresponds to this corresponds to this to this. I just map the 6 down. Here you see the graphs of the maps. Now here I have 6 maps, and I only had 4 before. So 2 are repeated, and you can see if you can see the repeated ones. I always find this a little tricky. But I think this one and this one look the same, for example, and there's another repeated pair. So now if I drop down this subinterval, it drops down to here. And I make a block on the diagonal. And what I see is there's just a little bit of leakage in that block. I take this subinterval, I drop it down. And so this subinterval is mapped to this subinterval. And I make a block and I have a small leakage. This subinterval is mapped to this subinterval. I make a block, I have a small leakage. So as I map these around, I have only tiny leakages. If I showed you the sequence and I said, please draw the blocks on the diagrams, it's not so easy to do. But you can find it automatically by computing these oscillated spaces. They automatically find the optimal long-term blocks from which you have the least leakage.
Sorry, Gary, just to make sure I understand. So you somehow computed those oscillated spaces. So the dark orange is what you use to produce these blocks.
Yes.
And then the maps that you plot are the ones that you're going to apply next.
Yeah, yes, I think
Yeah.
the T1 is the T omega corresponding to the phi omega.
That you will map for the next one. Yeah.
I guess so. Thrown out by omega.
No. I'm just trying to.
No, I guess this is no. I think it's correct. This is the interval that will under L omega. So that would be applying this map here.
Mm-hmm.
This interval will get mapped to this interval here. As you see this going to this, it's roughly in the same. It roughly stays where it is, and for that reason, this thing is on the diagonal. So it roughly stays where it is. But after that, they move around more. You can see this in a more complicated and non-rigorous setting. So this is a fluid flow on a cylinder. The flow essentially goes from left to right. The parameters of the flow are driven by Lorentz. So I have in the background, I have a Lorentz trajectory that's going around, and depending on, I forget exactly what, some function of the coordinates of Lorentz, I modify the parameters in my fluid flow. So it's a genuinely time-dependent system. And here I compute the oscillated space at, let's say, time 0. And again, I see these extreme positive and extreme negative, and the orange is essentially 0. What I do here is start pushing this forward. So I push this forward to 2.5 time units, 5 time units, et cetera, to 10 time units. What I'm doing in this last picture is I'm doing an independent computation of the oscillated space at time 10. And so I'm demonstrating here that these two things are the same. So this is the equivariance property. You can take this one, push it 10 units, or you can independently compute at the future time. So this is how they should behave. Below here, I have particle advection. So here I populate this with lots of gray particles, and I populate this with lots of black particles, and then I make some blobs nearby that are nothing special. And then I start advecting. Already this is 10, so maybe I blow this up a bit. So this is already 10, and then I go well beyond 10, so 20, 30, 40. And what you see is that these bigger blobs that were highlighted by the oscillated space, they get largely carried along. There's not much leakage, only a little bit filamenting out. But the other blobs that I just kind of chose randomly, they quickly mix. So the slow mixing that you see in the Lyapunov exponent, in the exceptional Lyapunov exponent, is connected with the slow mixing that you see in the state space. And if you were to try to find these objects in the state space using a state space method, that is very tough to do. But you get these things effectively automatically by looking at the oscillated space. Yes?
Do you know that your parameter needs to change every 2.5?
Oh, nothing special about 2.5.
You just randomly pick.
I mean, Lorentz is driving, right? So in the background, there's a much finer update. It's just I'm displaying, I just decided, I think probably because I wanted a 3x2 array of figures.
I guess I'm wondering, like, what if the driving force, like, it's not constant in time? Like, is it from data you can tell this is now what I need to switch to a different operator?
Yeah. Okay. Yes. So how rapidly how quickly your time? What's the right word? I mean, yeah. If your driving is fast, let's say, and having a big impact rapidly, then you need to update your LMAGs more frequently. If your driving is slower, or maybe the effect on the LMAGs is not so much, then you could afford to go a bit longer before you update your LMAGa. Yeah.
But that's like, there's no.
I mean, you mean if you're doing it from data or something?
Yeah.
I mean, you can. I think in low dimensions it's not too bad, because you can. I mean, if you're doing something like fluid flow, you can check how quickly the vector field is changing. If you're doing this in high dimensions, I'd have to think about it a bit. Okay, so did I talk about everything? I think I talked about everything up here. So maybe just some math details now. For that subshift of maps, okay, but just to tie this off, the index of compactness is log a third because they all had slope 3. You can estimate that the second Lyapunov exponent is log 0.84, which is much bigger than log 1/3. So this was an exceptional eigenvalue that we were looking at in these pictures here. Therefore important. And the rest is just describing, I think, what I already said verbally. Before I finish, I want to say that this is all for infinite time. And if you want to do things in finite time, which, well, often one does want to do, because if you're modeling the real world, there are natural timescales that you want to analyze things on. And maybe you don't always want to look at the infinite timescale limit. So in that case, the transfer operator methods are a little different. You look at singular values and singular vectors and singular functions of the transfer operator. Or actually, a very robust way of doing this is to take, maybe this doesn't make much sense, but to take a zero noise limit of what you would do in the transfer operator case, and you can get a differential geometric theory that uses a dynamic Laplace operator, and this is actually quite nicely adapted to data. And now you can also extend this to find transient coherent sets. So the coherent sets don't have to remain coherent for the full time window. They can come and go. So you might have a coherent set appearing and then disappearing. And you can also find this with time extended versions of these dynamic Laplace operators. And there are also similar things for transient almost invariant sets. So there's a whole separate literature that I don't discuss here for finite time computations. Okay, so in the remaining few minutes, maybe I'll just set this up. Wait, when did I start today? Quarter past. Right?
20 past. You take as long as you want.
So yeah, now I want to talk about stability of the spectrum. So I will concentrate, I guess, on the leading eigenvalue and its eigenvector, but also the other exceptional and isolated ones, and maybe just something to think about. So what sort of perturbations do I mean? Okay, so in dynamical systems, you might have a map and you might be perturbed to a nearby map. So this might represent model error. Maybe your T is a model and it's not quite correct. Or you might apply some stochastic noise to your map. So your map might be inferred somehow from, I guess what I'm going to say is like model error again, but you could have a noisy version of your map, which is effectively creating a stochastic dynamical system, and this will perturb your transfer operator. Or you might be applying, the perturbation might be due to some numerical method that you're applying, like Ulam, to estimate the transfer operator. So there are different types of perturbations that you like to consider, and you'd like to know something about all of these. So I'm going to now use this subscript epsilon. Epsilon is going to indicate the strength of the perturbation. And at least for this invariant measure, what we'd like to know first is that if we make such a perturbation, at least this perturbed operator has some unique fixed point. And then, if so, we would hope that as epsilon goes to 0, that this unique fixed point tends to the true fixed point. So yes, now for these 3 types of perturbations, results of perturbation of the map. Actually, I have to admit I forgot to come back to this. I'm sure there's some earlier results besides this in the expanding case for deterministic perturbations, but I was at the time struggling to think of what they were.
Some other one.
Something like this, yeah. So black was the name mentioned. For stochastic perturbations, there's some early work by, I think this one is black color, this is Elodie Young. And well, for numerical approximation, I mean, this goes back a long way to Lee's paper with Ulam. And there's obviously been a lot of work since then, trying to extend Ulam's method and these other perturbation results to broader class systems. Okay. Nowadays, I would say that there's this important work by Callan Nevarani that provides a general template for handling these perturbations, all these perturbations that I mentioned. And so I think I'm not going to, I think I'll just maybe get down to the assumptions here. So to set this up, suppose we're in the setting of theorem 1. That was the one where we had our Banach space B and we had the 2 norms. We had the norm that came with B, the double bar norm, and we had this weaker norm. So previously in BV, we had, say B is PV, and with the so the double bar norm was var plus L1. And the single bar norm was just L1, for example. Then you define this triple bar norm, it's a third norm, and it's something that's weaker than the operator norm. So what you do is you take the supremum over the unit ball in the strong norm, and you evaluate LF in the weak norm. If you were evaluating this in the strong norm, that would obviously just be the normal double bar operator norm. So it's something weaker than the operator norm, but it's sufficiently strong that you can get some perturbation results. The problem with the operator norm, I mean, if you could show that L epsilon goes to L in operator norm, that would be great. But often this is just not true for the sorts of perturbations that we're interested in dynamical systems. And on the plus side, this is often satisfied by the perturbations I've just talked about. Okay, so with that preamble, I think I'll stop there and get into that next lecture. Thanks. And since there are no questions, we can.
Yeah, I'll ask
something. Okay.
I'll ask one. So in the example where you have the map coupled to the finite to a subshift, is it rigorously known that the combined system is mixing?
You mean the random system?
Well, so you have a subshift which is its own system, and then a skew product, yeah. So
yeah, I mean,
it's
a subshift on 4 symbols, so it's a very simple.
That one is, but when you couple it to the map, potentially you could have invariant sets. So, for example, couple it to a constant. That's ridiculous, right? But if you couple it to something very rigid, it might not be mixing. Is it known that it's mixing?
In
Yes.
skew product, I think.
Yes, I mean the skew. Oh, you mean is the skew product mixing?
Yeah.
Okay, as you can see, this is from 2010, but I believe that that is the case. Yeah. You would. I mean, it would be very special if it were not.
I agree.
Because you're expanding here, so the only way you could really fail. I mean, if you're mixing, you're also exact, and in the phase space, and the only way something could go wrong is if there's some isolated piece.
Yeah, it would be very non-generic. I was just asking whether it's.
Yes.
You're right. Yeah.
The example with the weather forecast. So this is still a 1D map, right? So a scalar map into a scalar. How does that work with the two dimensions?
Weather forecast.
So can you show the picture with the weather forecast?
I don't know which was the weather forecast.
The one where you had
And in your
Okay. Oh, well, that was this.
yeah, I guess I don't quite understand how the problem is set up because you're only talking about 1D maps, right?
No.
Oh, this is not-
No, I mean, already I did Lorentz, right? So already I was out of the realm of 1D maps.
What's the dimension for the El Nino?
I mean, as many pixels as there are in the image.
You can find the item.
Yeah, because basically Enzo is a pretty strong signal. It's the next strongest after the seasonal summer-winter cycle, and a lot of the evolution is on some low-dimensional space, so it's not that hard actually.
But you work here in this observation space, so in 2D essentially. Single.
No. We construct the operator using the kernel in the high dimensional space, and then after we get the eigenvector, then we have this. We project back in some way to the 2D images, to the observation space. I'm happy to talk to people afterwards if they want to know more details.
Well, let's.
That's it. Thank you.